So for the next exploration, I want you to put these three functions into the graphing calculator. Again, you may need to push pause so you have enough time to do that. And of course, that when you're done putting them in, I want you to see if you can notice something about all three of them. So again, you can push pause to notice. Now if you have them in there, so you'll notice all the functions are pushed in here. If we push graph, hopefully you've had time to notice that sure there's some vertical asymptotes, but there is actually one thing that's similar to all of them. Now, I should comment on this. This is one of the problems with the graphing calculator. You see that line right here? That line actually isn't there. It's the calculator is having issues with the fact that you're dividing something really, really close to zero and you get an answer really, really close to zero and it doesn't know what to do. So that line there isn't actually part of the function. It's having trouble dealing with it. It actually looks like the asymptote for it. Same with this line here and this line here. So what we're trying to notice though is that each of these have horizontal asymptotes. So you see they all have horizontal asymptotes, like different vertical asymptotes, but horizontal asymptotes. So each of these all have horizontal asymptotes. Now the special part is they're all at y equals 0. So you see there's a horizontal asymptote there all the way through. None of these functions touch that horizontal line at y equals 0. So the question is, how could I have predicted that based on these equations? So if you have a chance to just look at it and study, you might see one of the reasons why this happens. And it has to do with the degree of the top and the bottom. So if you look at this one, for example, the degree of this is 2. And the degree of this one is 4. So I want you to notice the degree of the other ones and see if you can notice a pattern. As you're thinking about that, you can start to make this note. Horizontal asymptotes indicate the end behavior far off both sides of the graph. So the graphs never cross vertical asymptotes, but they may cross horizontal asymptotes. That's one thing that's different. That's why when we're talking about horizontal asymptotes, we're talking about the spots way out on the left side or the right side, so like positive infinity and negative infinity. That's where I'm interested in looking at the asymptotes. Locally, around the graph, you might have a situation where the graph actually crosses, and if you look closely, if we just showed you this one, this graph actually crosses the horizontal asymptote, but out at the ends, it doesn't. I think I can probably highlight just that one. Oh, no, that's the wrong one. Go to y equals. We'll hide this one, and we'll look at this one. So there you'll see what it's trying to show you is the graph comes and it actually goes down at this spot. So it does cross the horizontal asymptote here, but at the ends, at the far extremes, it doesn't. And that's what this horizontal asymptote can do. And I've already given you the hint that you can find where the horizontal asymptote is by comparing the degrees of the numerator, which I'm going to call n, and the denominator, which I'm going to call m. So if we go back, what do you notice about the degree of the top versus the degree on the bottom? You might talk to your elbow partner, but hopefully you've noticed that the degree on the top is always smaller than the degree on the bottom. So the degree on the bottom is the bigger one. So this one has a degree of 2, this has a degree of 1, so the bottom is bigger, and we end up with a horizontal asymptote at y equals 0. Even this one, the degree in the bottom is 1, the degree in the top is 0. So the question is, why is that? Well, if we just look at a simple situation like x squared over x cubed, this is a rational function. Think of x values. If you put in something like 100, and you square it, and you go, wow, that's a pretty big number. But if you put in that same one on the bottom and you're cubing it, it's really big. So regardless of that this is big, you're dividing by a really big thing, because cubing a number is much, much bigger than squaring a number. And so what happens when you have a big number? Let's say you had 100. Well, in this case you have, what is it, 100,000? That's great, but compare it to 100 to the power of 3 and you get a much bigger number. So even though 100,000 is pretty big, sorry, the top should be 10,000. The bottom, because you're cubing it, is really big, which means this becomes a fraction with a really big denominator. And as you get bigger and bigger values for x, so now try and consider if you put in 1 million squared divided by 1 million cubed, you end up having a really, really big number on the bottom and a somewhat big number on the top. And we know fractions, when the number is really big on the top, on the bottom, and the number on the top isn't quite as big, this is almost 0. Even if I change this to like 10 over 77 is a small decimal. 10 over 777 is even smaller. And 10 over 7 million is almost 0. So when you have a degree on the bottom that is bigger than the top, when you put in huge numbers, they're always going to go almost to 0. They're not going to go exactly to 0. That's why it's a horizontal asymptote. And so our first conclusion is this. If n, which is the degree on the numerator, is less than the m, the degree on the denominator, then the horizontal asymptote is at y equals 0. So I want you to clear. So go back here, clear these out again. We're done looking at those three. I want you to put these three functions in and then see what you notice about these. So hopefully you've had a chance to put them in and examine it. So I'm going to graph and see what happens on these ones. So that one looks very similar, but it's moved up. So the horizontal asymptote's changed. The second one, horizontal asymptote, seems to be up as well. And so it turns out for each of these, the horizontal asymptote now is up here. Okay, you see there's a horizontal asymptote up there, and it looks like it's around 2. So what you hopefully would notice on these is that each of them have a horizontal asymptote at y equals 2. So the question is, why is that the case? Well, again, it has to do with comparing the degrees. When we looked at these, you see the degree of this is 1 and 1. So it's not like the one before where the degree was bigger on the bottom. This, the degrees are the same. In this one, if you look, the degree here is 2 and the degree here is 2. So they're the same. And here, the degrees are the same. So it turns out that if the degrees are the same, the horizontal asymptote is not at y equals 0, it's someplace else. But the question is, why is it at 2? Well, it has to do with the leading coefficients. So if your n and m are the same, so if n equals m, then look at the leading coefficients. Now, we're going to make this note later, so you don't need to write this down right now if you don't want to. So look at the leading coefficients. So you'll notice in the first one, it's 2 over 1. So 2 divided by 1 is 2, and the horizontal asymptote was 2. In B, it is 4 over 2, which is 2, and the leading coefficient, or the horizontal asymptote at 2. And for C, we had 16 as 8 as the leading coefficients. Divide those, you get 2. So it turns out that for the third part, what you do is, or sorry, for this third example, if n equals m, then the horizontal asymptote is found by taking the leading coefficient on the top divided by the leading coefficient of the bottom. Whatever that number is, that's where the asymptote is. So I'll give you a second to write that down. Pause if you need to. So the question is why? Well, again, let's look at this. If we take, for example, in B, if we put in a number like 1 million, oops, 1 million. If we put in 1 million for x, you're going to square it. That's going to be really big. And then you're going to multiply by 5. So, or sorry, by 4. So it's 4 really big number. You put that 1 million in here on the bottom, and you multiply by 2. Well, that's the same really big number. It's just multiplied by 2. Now, this little -2 isn't going to really have much influence on this. If you're talking a billion, if you subtract 2, big deal. Or if you add 1, big deal. Okay? So if you look at it, essentially this number here, which is a million squared, -2, whatever, and this is a million squared, plus 1, well, it's essentially the same. Those are so big that they're pretty much the same, and they kind of cancel out. And you're left with the fact that the top is 4 times bigger, or sorry, 4, and this is 2, so it's 2 times bigger. And as a result, your asymptotes are going to be at x equals 2. And it doesn't have, even when you put in a smaller number like 10, if you put in 10 and squared it, so that's 100, times 4 is 400, -2 is kind of small. And then on the bottom, put in 10 squared is 100 times 2 plus 1. So essentially is about 2 when you actually do this math. It's 398 over 201. Well, that's almost 2. Okay? So that's why you only look at the leading coefficients in this one. So that's our second conclusion. And on the next video, we'll look at our third.